The ground under your feet feels permanent, solid, eternal. It is none of those things. Right now, as you watch this, one of the world's largest land masses is slowly, silently, inevitably splitting in two. Not in a million years, not in some distant geological fantasy. The process has already started. We have measured it. We have watched it accelerate. And one unforgettable September morning in 2005, the Earth stopped being subtle about it. What you're looking at is the birth of a new ocean, and we are alive to witness the opening chapter. September 14th, 2005, northern Ethiopia, the Afar Depression, one of the most geologically violent places on the planet. For days, the ground shook. Not once, not twice, over 100 earthquakes in a single week, each tremor marching along the same invisible line, a line that was quietly, systematically opening in the earth beneath. Then, on September 26th, the Dabahu volcano erupted. It wasn't the most powerful eruption in recorded history. Krakatoa it was not. But what it did, what it revealed, was something scientists had theorized for decades but never seen so clearly with their own eyes. In a matter of days, the desert floor tore open. 60 kilometers of fresh fissures, some of them several meters wide and deep, split across the landscape like a slow-motion wound. Heat shimmered from the breaks. New rock cooled where magma had forced its way to the surface. Villages emptied overnight. 6,000 people fled on foot, leaving behind livestock, fields, and wells, everything they owned. For the people of Afar, it felt like the earth had simply lost its mind. For scientists, it was the clearest signal they had ever received. The plates weren't locked. They were moving, and the crust beneath East Africa was thin enough, weak enough, and hot enough to fail. GPS stations were rushed in. Satellites turned their gaze downward. Seismic arrays lit up with data. What they confirmed would reshape how we understood this entire continent. East Africa was not just shifting, it was breaking apart. To understand what is happening, you need to zoom out, far out. Picture a scar running nearly 3,000 kilometers down the eastern edge of Africa, starting in the Afar Triangle of northern Ethiopia, one of the lowest, hottest, most extreme places on Earth, and cutting south through Ethiopia, Kenya, Tanzania, all the way down to Mozambique. This is the East African Rift System, and it is not a single crack. It is a zone, a wide fracturing corridor where the Earth's surface stretches, buckles, and drops. In places, it splits into two arms, eastern and western, like a river that can't decide its course. Towering cliff walls frame deep, flat basins. Lakes Tanganyika and Malawi fill some of those basins, among the deepest lakes on the planet, sitting in valleys that only exist because the ground beneath them is slowly sinking. The driver behind all of this is heat. Deep in the mantle, the thick layer of rock beneath Earth's crust, an enormous plume of superheated material is rising, like a massive, invisible blowtorch pointed at the underside of the continent. As this hot rock pushes upward, parts of it melt. That melt forces its way into the crust, wedging the two great tectonic plates, the Nubian plate to the west and the Somali plate to the east, further and further apart. Year by year, the separation is tiny, a few millimeters. You wouldn't feel it, you couldn't see it. But geology doesn't need you to feel it. Over millions of years, those millimeters add up to something staggering. Faults slip, rock blocks tilt and slide downward, valleys form, lava cools into new crust, and the whole system, this slow, grinding, relentless engine of planetary change, mirrors exactly what happens at the bottom of the ocean, where mid-ocean ridges build new seafloor every single day. The East African Rift is one of the only places on Earth where that deep oceanic process is happening on land, where we can actually see it, walk on it, and measure it with our own instruments. Some parts of the Afar region already sit below sea level. The crust there has thinned so dramatically that lava oozes out in long, curtain-like flows. The landscape is otherworldly. Boiling springs, lava lakes that never cool, wide salt flats that stretch to the horizon. Extreme, beautiful, violent. A preview of what's coming. The birth of an ocean doesn't happen in a single moment. It follows a sequence, a planetary recipe, if you will, that plays out across deep time. Stage 1. The Rift Valley. The crust stretches, faults multiply. The land drops in long parallel blocks, forming valleys with steep cliff walls. This is where East Africa stands today. It is the very first page of the story. Stage 2. The Gulf. Over time, the lowest sections of the rift drop far enough that water begins to invade. Narrow fingers from the Red Sea or the Indian Ocean seep in, slowly at first, then more persistently. The sea claims new ground. A long, thin arm of ocean forms where once there was only desert. Think of the Red Sea, that narrow body of water between Africa and the Arabian Peninsula. It didn't always exist. It opened in exactly this way, starting as a rift valley, much like what we see in Afar today, and it is still widening as you watch this. Stage 3. The Ocean Basin. The two separating plates continue to drift apart. A line of underwater volcanoes rises down the middle, building a mid-ocean ridge. New seafloor spreads outward from that ridge. The gap widens, deepens, fills. A genuine ocean with shores, currents, and depths measured in kilometers takes its place on the map. That is where this is headed. Scientists estimate it will take between 5 and 10 million years for a true ocean to form in East Africa. In geological time, that is not very long. The Atlantic Ocean took tens of millions of years to open after the supercontinent Pangaea broke apart. The Red Sea, younger and narrower, started in an almost identical setting as Afar today, and it is still widening as you watch this. We are watching the very beginning of that same story, but this time with instruments that can measure every millimeter of it. Here is what makes this era of geology unlike any that came before it. We can actually see it happening. GPS stations bolted directly into bedrock detect plate movement as small as 3 millimeters per year. 3 millimeters, the thickness of 2 stacked coins. And they catch it year after year, confirming the steady, patient separation of the Nubian and Somali plates. Satellites equipped with radar, using a technique called INSAR, or Interferometric Synthetic Aperture Radar, compare images of the same patch of ground taken days apart. The result? Maps of ground deformation so precise they can detect magma moving deep underground before anything breaks at the surface. Thermal sensors identify hot zones near the surface, early signs that lava is rising. Seismic arrays spread across the rift listen for swarms of tiny earthquakes, tracing the exact paths of magma intrusions and fresh fault slips. Taken together, this flood of data feeds into computer models that simulate how the plates move, how the crust fractures, and where the next rupture is likely to occur. Machine learning algorithms scan satellite imagery and seismic noise for patterns invisible to the human eye, giving scientists an early warning system for eruptions and ground failures that simply didn't exist a generation ago. The 2005 Debahu event pulled geology out of the textbook and into people's living rooms. Since then, the rift has not gone quiet. Smaller magma intrusions and fault slips continue all along the system. The region has become quite keeps coming. But this isn't just a story about rocks and satellites. Millions of people live on this rift, and they have, for thousands of years, built lives on some of the most geologically restless ground on Earth. The Afar people of Ethiopia and Djibouti have developed practical knowledge that scientists now study seriously. They know which volcanic rocks are fresh and brittle, dangerous to build on, and which are old and stable. They have learned to read the land's moods in ways that no instrument can fully replace. And the rift, for all its danger, offers something remarkable in return: geothermal energy. Steam rising from the Earth's own heat, captured and converted into electricity. Ethiopia and Kenya already run geothermal power plants drawing from rift fields, generating clean, low-carbon electricity that powers cities hundreds of kilometers away. These plants are expanding. The rift's restless heat, reframed, becomes a resource. Volcanic ash over time breaks down into some of the most fertile soil on Earth. Where there is enough water, rift farmland yields abundantly. The risks are real too, and they must be stated plainly. Earthquakes crack roads and collapse buildings. Ash clouds choke rivers and crops. Lava flows can sever supply routes in hours. These are not hypothetical threats. They are lived realities for communities across Ethiopia, Kenya, Tanzania, and beyond. The difference between a catastrophe and a managed crisis often comes down to one thing: how good your monitoring is, how fast your warning systems work, how seriously your infrastructure was designed with these hazards in mind. The rift isn't going to stop, but good science, good planning, and genuine partnership with the communities who live here can change what it means to live on shifting ground.
Now close your eyes for a moment. Come back in 5 million years. The map of Africa looks different. A narrow blue arm of ocean cuts into the Horn of Africa, stretching from the Red Sea deep into the continent. On its eastern shore sits a long, new landmass, a great island carved from what was once Ethiopia, Djibouti, Somalia, and parts of Eritrea and Kenya. Think of it as Africa's answer to the Arabian Peninsula, a piece of continent that pulled away to open a new sea. On the western shore, the rest of the African continent holds its ground, its coastline redrawn, its rivers rerouted, its climate changed by the presence of this new body of water. Mangrove forests and coral reefs grow where today there is only scrub and cracked earth. New fisheries form. Port cities rise on shores that don't yet exist. Trade routes emerge across a sea that hasn't been born. Ecosystems split along with the continent. Isolated populations evolve into distinct species, the same process that turned Madagascar, which broke away far earlier, into a biological island of wonders found nowhere else on Earth. Climate shifts. A large body of water changes winds. Coasts near the new sea grow cooler and wetter. Interior plateaus dry out. Agriculture adapts. Human civilization adjusts, as it always has, to the new geography of the planet. None of this happens in a human lifetime, or 10 lifetimes, or 100. It unfolds across timescales that make recorded history look like a single afternoon. But here is the point. We can see it beginning. We have the instruments to measure it. We have the models to project it. We have the awareness, for the first time in our species' existence, to watch a continent be reborn in real time. The 2005 Dabahu eruption was a wake-up call. Not because it was the largest, not because it was the deadliest, but because it made something undeniable. The ground is not permanent. The map is not fixed. The world you were born into is not the world that always was, or the world that always will be. Every map is a snapshot, a photograph of a planet that never stops moving. The Atlantic Ocean was once a rift valley, just like East Africa's. The Red Sea was once a desert that cracked open. And one day, In a future so distant that our entire civilization fits inside a rounding error, a child will pick up a globe and see two Africas separated by a sea. When that day comes, they will be looking at the ending of a process we are just now watching begin. That should not make you feel small. It should make you feel exactly the opposite. We are the first species on this planet to understand in real time the forces that are reshaping it beneath our feet. We can measure them, predict them, prepare for them, even harness them. The Earth is alive, and we, for the first time in 4.5 billion years of this planet's history, are paying attention.